assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
For this example, we have a coil of 950 turns that is sitting in a uniform constant magnetic field. And initially, the surface normal of our coil is perpendicular to the magnetic field. So if we were to look at that in a view above our coil here, it might look something like this. Here is our loop, here is the normal, and maybe our magnetic field points in this direction. And then what we're going to do is in 0.01 seconds, we're going to turn it by 45 degrees. So if this is the initial setup here, we'll end up with something like this, where there's our loop from the above view, where its normal now points like this, and the B field is still in this direction. So we can see that our surface normal there is going to make an angle of 45 degrees with our magnetic field. So what we want to do is, given that we know what EMF is induced in our loop in this time period, we want to determine what the strength of the magnetic field has to be. So if we just recall, Faraday's law of induction states that the induced EMF in our loop here is going to be equal to minus the number of loops we have times the change in flux in a single loop over the change in time. Alternatively, we could exclude this n here for the number of loops and just remember that it's included in our flux. But we'll just pull it outside to make things a little easier on ourselves. Okay, so initially, we can see that since the magnetic field is going to be perpendicular to our surface normal, that there should be no flux in the initial setup. So when we expand our change in flux to be the final flux minus the initial flux, we know that the initial flux is going to be 0. However, the final flux is not going to be 0. It's going to be equal to our general expression for the flux, which is B times A times the cosine of the angle between the magnetic field and the surface normal, which in our case is just going to be phi, which is 45 degrees up here, which is this angle we drew right here. Okay. So knowing that, we can plug that into our equation here for the induced EMF. We'll have that the induced EMF is minus n over delta t times BA cosine theta, or cosine phi. And A is going to be the area of a circle with radius 0.06 meters. And we know that the area of a circle is just pi r squared, so we can just substitute that in there as well. We'll have minus nb pi r squared cosine of phi over delta t. All right. So now we're at a point where we should have everything we need to just start calculating. We have 950 turns. we have the strength of the magnetic field is unknown. So that'll be our one unknown, and then everything else is known. Yeah. Okay. So let's go ahead and solve this equation for our unknown. So we'll multiply both sides of our equation by delta t. And we'll have delta t times E equals minus nb pi r squared cosine of phi. And then we'll divide both sides of our equation by everything that's not b. We'll have b equals delta t times E divided by, there's an n, a pi, an r squared, and a cosine of phi. Okay. And we do have a minus sign in this, but since we're just looking for the magnitude of the field, we can just ignore the sign. All right. So now we should be able to just plug in all our values. And if we do that, we will get that the magnitude of the magnetic field is 8.6 times 10 to the minus 5 teslas.